From a distance, Uranus presents a serene, featureless shell, but beneath that uniform calm lies a world defined by violent, asymmetric physics. Discovered in 1781 by William Herschel, Uranus is an ice giant. Unlike the gas giants Jupiter and Saturn, which are primarily hydrogen, the bulk of Uranus's mass is composed of a volatile rich mantle of water, ammonia, and methane ices. Before we roll into the terrifying physics of this ice giant, take a quick second to hit that subscribe button so you don't miss any of our deep space journeys. All right, let's dive back in. In our solar system, planetary rotation follows a strict baseline. Most planets spin upright on their axes, rotating like tops as they travel their orbital paths. This 3D orbital diagram models the anomaly. While the standard gas giant spins vertically, Uranus possesses an extreme axial tilt of 97.77 degrees. It rolls entirely on its side, practically tumbling along its orbital track around the Sun. Planetary formation models show that a 97-degree tilt cannot occur spontaneously during accretion. This physical configuration suggests a massive external force intervened to alter the planet's mechanics. Astrophysical models point to the cataclysma giant impact hypothesis. During the early formation of the solar system, an erratic protoplanet roughly twice the mass of Earth suffered a catastrophic off-center collision with infant Uranus. This specific kinetic strike physically knocked the entire planet onto its side. As we will see, it also deeply disrupted the ice giant's internal thermodynamics. Pushed out to its current position, Uranus now completes a massive 84 Earth-year journey around the Sun. Because the planet maintains that severe 97-degree tilt throughout its orbit, it experiences extreme 21-year-long polar seasons. This top-down orbital map reveals the severity of those seasons. For more than 2 decades, one pole points directly at the Sun, absorbing continuous sunlight, while the opposite hemisphere is plunged into total, freezing darkness. The cataclysma impact provides a single physical origin for the planet's axial tilt and thermal state. This one event established the parameters for its current architecture. Leaving the macro scale of orbital mechanics, we can analyze the planet's architecture by descending directly through its upper atmosphere. The atmospheric baseline is largely what you would expect from a giant planet: 82.5% hydrogen and 15.2% helium. The defining variable sits in the upper cloud decks. Here, we find a critical 2.3% concentration of methane gas. Looking at this atmospheric schematic, the optical physics become clear. When full-spectrum solar light hits the atmosphere, the methane molecules absorb the red spectrum entirely. The remaining cyan and aquamarine wavelengths scatter and reflect back into space. At nearly 3 billion kilometers from the Sun, Uranus receives less than 1% of the solar energy that reaches Earth. Despite this weak external solar input, zonal winds in the upper decks reach 900 kilometers per hour. Solar radiation is too weak to drive these velocities at such a great distance. These winds are instead powered by internal pressure gradients and the planet's internal thermodynamics. Plunging beneath those outer gas layers, we reach the planet's dominant mass, a dense superionic fluid mantle of water, ammonia, and methane ices. This cross-section graphs the internal descent. Deep in the fluid mantle, the thermobaric gradients reach severe thresholds. Temperatures climb past 2,000 degrees Celsius, and the pressure exceeds 100 gigapascals. Under these intense physical parameters, the chemical bonds of the methane molecules can no longer hold. The molecules violently vibrate and dissociate, breaking apart into isolated carbon and hydrogen atoms. Crushed at a pressure, those newly isolated carbon atoms seek stability. They bond together, crystallizing into rigid, solid structures, diamonds. These dense crystalline structures then sink. Uranus experiences a literal diamond rain, with millions of microscopic solid diamonds constantly precipitating downwards through the fluid mantle. As this immense mass of diamonds sinks toward the core, it releases massive amounts of gravitational potential energy in the form of friction and heat. High-pressure phase changes in the mantle create a chemical environment distinct from the hydrogen-heavy interiors of standard gas giants. Below the fluid mantle rests a relatively small, rocky core composed of silicates and iron. Here, planetary scientists encounter the ice giant paradox, a complete absence of expected heat. This bar chart compares thermal emissions. Neptune, a structurally similar ice giant, radiates 2.6 times the heat it receives from the sun, but the thermal emission of Uranus flatlines near zero. It radiates almost no internal heat into space. Without an active internal heat flux warming the surface layers, Uranus hosts the coldest planetary atmosphere in the solar system, dropping to a minimum of -224 degrees Celsius. To explain this severe thermal anomaly, physicists look backward to the cataclysma impact. The prevailing thermodynamic model suggests the ancient collision disrupted the mantle, creating stratified convective boundaries. These deep fluid layers act as a dense thermal blanket, preventing convection and permanently trapping the planet's primordial heat inside its core. Uranus functions as a massive thermal reservoir. Its lack of emission suggests that deep internal boundaries are effectively sealing the planet's primordial heat within the core. That internal insulation also dictates how the planet generates its magnetic field. By standard astrophysical baselines, a planetary magnetic dynamo originates directly from the physical center of the core and aligns roughly with the planet's rotational axis. This wireframe diagram maps the primary anomaly. On Uranus, the magnetic axis is tilted a massive 59 degrees away from the rotational spin axis. Compounding that is a second, highly irregular structural anomaly. The origin of the magnetic field is not in the center of the planet. It is physically displaced downward by a full third of the planetary radius. This non-dipolar, offset configuration generates a highly asymmetrical magnetosphere that bulges outwards on one side and compresses tightly on the other. Because Uranus spins on a 97-degree tilt, this irregular magnetic field twists, tumbles, and violently wobbles as the planet rotates through space. As the solar wind hits this tumbling architecture, the magnetosphere opens and closes unpredictably, creating chaotic interactions that force physicists to revise standard models. Pulling outward from the core, the extreme physics of Uranus extend directly into its orbital neighborhood. Uranus is encircled by 13 narrow, dark rings. Locked into the planet's extreme 97-degree tilt, these dense fields of carbonaceous ice chunks orbit vertically, resembling a massive cosmic bullseye. Orbital dynamicists suspect these rings are the shattered remnants of an ancient moon, destroyed by the planet's intense tidal forces. Beyond the rings orbit 28 known moons, traditionally named after Shakespearean characters. Their geology is deeply varied, ranging from the young tectonic fault lines of Ariel to the ancient, heavily cratered impact basins of Umbriel. The most extreme example of this chaotic geology is found on the moon Miranda. Miranda's surface is violently fragmented, featuring Verona Rupes, a vertical cliff drop 20 kilometers deep. The moon resembles a jagged jigsaw puzzle, and planetary scientists hypothesize it was shattered by a massive impact before its gravity slowly pulled the fractured pieces back together. The Uranian periphery is an orbital graveyard. Its entire ring and lunar system is defined by a history of severe tidal destruction and violent reaccretion. Every thermodynamic and magnetic model we have mapped is limited by a lack of raw data. Humanity's baseline understanding of this ice giant relies on a single brief encounter. In January 1986, NASA's Voyager 2 probe executed the first and only close flyby of the Uranian system. Modern astrophysics is currently attempting to build comprehensive structural models based entirely on a few hours of data captured decades ago. To solve this, the science community designated a dedicated flagship mission to Uranus as top priority, the Uranus Orbiter and Probe, planned for the early 2030s. The UOP mission will execute a multi-year orbital study and plunge an entry probe deep into the icy cloud decks to test these thermobaric gradients. The cosmos is full of anomalies, and Uranus leads the pack. Next time, keep looking up.